So why might an RTOS be useful to you, right? First of all, I would say not all applications warrant the use of a real-time kernel. You can make perfectly good designs using a Superloop foreground background type architecture. I've deliberately graded these out. You're not supposed to read what's in this. The idea here is just to show that here's a piece of functionality with a state machine or a flow chart or something. Here's another piece of functionality. Here's another piece of functionality. And the microcontroller is just looping round and round, running this, running this, running this. There's interrupts going on. I think we're all familiar with this type of architecture. And for a lot of applications, that's perfectly adequate, especially the smaller applications. If there aren't any communication interfaces, there's no asynchronous interfaces and that sort of thing, it's perfectly acceptable, perfectly maintainable. But will it scale? Will it scale to larger applications? Or if you add functionality in, or if you change the hardware, is that kind of design going to make your life very difficult as the product evolves? As all products do. I'm sure anyone with more than a couple of years of experience will be familiar with that. So here are a few items that can be problematic trying to scale up a Superloop type design. And here what we want to do is turn all these sort of grumpy faces into smiley faces. So things like tolerance of hardware change. Well, the Superloop is not that tolerant. It's not particularly bad, but if the rate at which you're looping is dependent on the hardware, the speed of the hardware, the clock, then it's not that great. Things like code reuse are very hard because your bits of functionality are very, very independent and interworked. I'm not going to go down the list of all of them, but I'm just trying to show some of the attributes that we're trying to improve. And the problem here can be summed up by saying that there's a big interdependency between what your application is trying to do functionally and how your application is running, the timing of your application. So really what we want to do is break that to make our application much more maintainable. So we want to take the timing, if you like, as one aspect that the real-time kernel can control and remove that from what we're trying to write functionally. So if we break our application up into separate tasks, different threads of execution, if you like, then we might have a structure like this. Here's a periodic task. We want to delay until it's time to run again, perform some kind of function, control function, whatever, output the results, go back and delay again. What we have here for this delay is in a real-time kernel structure is to actually make a call to the real-time kernel and say, I don't want to run again until it's time to run again. The real-time kernel is then responsible for the timing and say, okay, now it's time to run again. I'm going to unblock this task. The task can run. So the structure of the task becomes very, very simple. And you can rely on the real-time kernel to make sure that it runs the right tasks at the right time. So you can assign a priority to this and say, this is my primary functionality, or this is my safety functionality, or something like that. This is really important. This task over here, which is waiting for an interrupt and processing data, is maybe less important. Actually, probably a bad example, because the interrupts are probably the most important. Some kind of background processing, which is just a forever loop, that's not really important. So we'll assign that a low priority, that a medium priority, that really high priority, and then the kernel will make sure that that runs absolutely when it's supposed to. You can change the speed of the hardware, won't make a difference. You can add more code into this background task as the functionality grows, as it inevitably does, it won't make a difference. This is still guaranteed to run. So it's much more maintainable. Because you're relying on the services of the kernel to do all your signaling and timing and communication, and you're left with autonomous, functionally cohesive tasks which are doing just executing one very specific piece of functionality. So now If we look back at our attributes here, things like tolerance of hardware change, I've already said is very tolerant of hardware change. Code reuse becomes much easier because you don't have this interdependency between different pieces of functionality. You can mix hard and soft real time just by assigning priorities and that sort of thing.